this video we will continue with our discussion on genetic algorithms, and importantly we will look at what are all the challenges in representing data so that it is readily amenable for a genetic algorithm, and we will also look at an illustration or a simple example to see how one can potentially use GAs and how they can lead to convergence to the desired minimum. Again let me call this yes, right. So, this is a very interesting representation for a relatively complex system which is called so the representation is Cartesian, it is called genetic programming for evolvable hardware. So, let us say you have a system like this, it is a 2 by 2 array of gates, right. So, I am just giving this is not a very germane example to what we are studying here, but it will give you an idea of how do you creatively construct representations for a difficult search problem. This is what you need to do if you are working with genetic algorithms, right. So, what do you do? So, what gate is this? AND or NOR NAND, right. So, let us call these let us have a list of gates OR AND XOR NAND NOR. Any other gates commonly used? You have XNOR, I guess. Not. Yeah, I am trying to restrict myself to 2 input gates, right. This is input 2, this is input 3, this is input 4, this is I will call this 5, 6, 7, 8 and O1, O2. Something of this sort, right. So, now I need a representation. So, I can go and evolve, let us say I should follow a particular truth table. So, I am going to find a function that does, I am going to find a gate arrangement that does something, right. So, this is actually how people evolve certain very complex circuits. Here is a very interesting, it was done by Adrian Thompson back in 1995. Right. And what they found was evolutionary algorithms were taking advantage of things that normal designers do not do, because it is a more blind thing, right. So, it essentially tries to tap into a very different portion of design space even, right, because the way so in fact somebody else was mentioning to me recently you should go and look up the NASA evolutionary designed antenna. It apparently looks very ugly, but it is very effective. It has got a very weird shape because it was evolutionary design, it was not designed by a designer, but the antenna is still very effective because well it was optimized very carefully. So, how do you represent this? I can represent every gate by let us start with this. So, I would say 1, 2 AND then 3, 4 NAND then 5, 6 OR then 7, 8 NOR. I could stick all these into a row, that is what we call a Cartesian representation, and I will say and I will replace it by 2 or I will replace it by 1, NAND I will replace it by 4, NOR I will replace it by 5. So, a representation for this gate would be, and my outputs are, so I will call this O3, O4, O1 and O2. In fact, I do not even, yeah, I need to just come up with some way, right. So, I could call this 5 and 6 or whatever, the what output goes into the next one, right. So, I need to give this a number 2. So, these are the inputs that are going in here, this same input is also going here. So, I would call so this actually will not be 7 8, this will be 7 4 and not 7 4, it will be 6 4, is that right? So, this is I call these the so just think of, you just need to come up with your you know a systematic rule for representing, right. If you have an m cross n array, right, if I say 5, I know where it is. So, if it is a 3 cross 3 array, I know it will be in the second row second column, that will be 5, right. If it is a 6 cross 6 array, I know it will be in the first row fourth column, something like that. So, I just need a long representation which now says what is the input to each gate, what is the type of the gate, input type of the gate, input type of the gate, and finally what are the outputs. Now all I have to do is I can just go and mercilessly change things here, I will get new gate configurations, I can simulate them and I can see which am I getting a better function or not. For that what will I have to do? I have to do fitness and all that stuff. So, we will have to go back to all of these concepts.
Changing, you will not change output gate, output well, only the
You could. I will now take output from the second gate itself, maybe, I do not know. I could take any of these and connect it to output.
Okay.
I may just ignore this.
Okay, you just want the truth table, doesn't matter where you take the output.
Yeah, you just want the truth table to follow whatever truth table you have set. I might want a circular shift function, meaning if I give B1, B2, B3 as input, I need to get B3, B1, B2 as output. That is all. Any bunch of gates, any output, whatever does this job, I am happy with it. This is actually very interesting if you go and look this up, because in fact we did a study back in 2011 where we showed that we can this is something we will discuss in the very end of the course when we talk about robustness and evolvability. So, we showed that we could actually design robust electrical circuits as well. So, these are typically can be easily implemented on FPGAs. FPGAs are field programmable gate arrays, meaning they are not set in set in stone as an AND gate or an OR gate or something like that. Using a configuration string, they can be dynamically reconfigured as an OR gate, an AND gate and so on. So, you take this particular string potentially, you have to do a lot more work than that, and you feed it to that FPGA, it will now take up, assume this circuit. You change the string, it will assume a different circuit. So, it can reconfigure itself. So, can you design a circuit that can easily, from making just a small rewiring, convert itself from computing a circular shift to a right shift? Or you can even think of more harder functions, right. So, if you really were to extend this, can you build a reconfigurable robot? Right, because it is a very popular application. There are some reconfigurable robots that people have built for, say, deep sea exploration. Right? Sometimes it has to sneak under Titanic. It will just it will crawl and go. It will be walking as a biped till then, but then it has some real obstacle in the way. It will reconfigure, become a reptile and crawl through, something like that. So, there is some example of this sort, but basically how do you design such circuits? Because the search space is so large, you have to really resort to some very intelligent algorithms, and evolution seems to work very well with a very large search space, right. That is sort of the observation that we have from observing years of biology, right. Evolution seems to work well in practice, right. So, why does it work? There is a selection pressure, right, and there is some notion of fitness, and then you basically you actually do not worry about how evolution happens in real life, right. So, you might have heard on we basically mostly agree with the Darwinian theory of evolution. There is also the Lamarckian theory of evolution. As far as GAs are concerned, you are as happy with the Lamarckian theory as with the Darwinian theory, as long as it can give you better results, right. That is all you really worry about. So, if you look at this framework that we are talking about, how do we go about and compute each of these things? So, let us take Another simple example. So, now I think you have some idea of how would you do for scheduling, you just need to establish these operators, and how would you do it for a bunch of electrical circuits. If you look at a very simple example, let us say I want to solve x square equals 9, you already know the solution. Let us assume that the solution is only in integers, right. So, I will have to now assemble a bunch of candidate solutions. So, x square equals 9, let me say I will use 4 bits to represent the solution, maybe 3 RM, or I will use 3 bits to represent the solution, right. So, my possible solutions are these. Many more, right. Let us just start with some subset of this. So, I establish my population size, I take it as 4, right, and the numbers I use are 0 0 0, 0 0 1, 1 0 0, 1 1 1. I have carefully left out the solution from this, but let us say this is our initial population. Now, what do you do?
Evaluate x square.
No, before that you evolve, you mutate, right. So, let us say I mutate this bit, okay, so it becomes 0 0 1, and let us say here I mutate this bit, this will become 1, oh wait, I do not want to get to the solution, let us mutate this bit, so it becomes 1 0 1. No, you do not care, it is random, it is blind, that is very important, right. So, that comes back to a question that you were asking yesterday, what is parallelizability? Just parallelly do this, throw it to 100 cores, just change it, you do not care what is happening. All you care is I will now generate some large number of individuals, I will again squash it to the original population size. Finally, I have to somehow come back to n equal to 4, right, I do whatever, right. So, this 1 0 0 might probably become 1 1 0, then 1 1 0 may become 0 1 1, right. And let us do a few crossovers, let us cross over 0 0 1 and 1 0 0, and we might get a 1 0 1 again from that, and let us cross 1 1 1 with 0 0 0, you will get 1 1 0, let us say. This is a very small example, so you are not going to get enough variety. First of all, your space has only 8 numbers, right, but given this, so now we have 6 individuals, squash it back. In fact, you should, there is a very systematic way to do this, you might actually end up with exactly 8 individuals or something like that. So, you will end up with 8 individuals, you do 2 mutations and 2 crossovers or something like that, and including the parents, you will have 8 individuals. Now, you compute the fitness for each of these. What would the fitness here be?
Error square from 9.
So, it may be something like, but closer to 0, higher the fitness. Because your best solution is x equals 3. So, 3 square minus 9 has the highest fitness. So, you maybe want to do 1 by x or something, or you can do minus whatever. Let us just say 1 by x, right. So, 1 by x squared minus 9 is my fitness value. So, this is 1, so it will be 1 by 8, and I can take absolute value also, it does not really matter. So, then this is, what is this? This is 5, you know. So, 1 by 16, this is, what is this, 6. So, this is 1 by 27, this is 3, okay, you have infinity, I did not want this, let us leave this out, right, because you want to do more iterations, and this is again 1 by 16, this is again 1 by 27. How do you pick the best solution now? How do you pick the new population now?
Parent also you have to evaluate.
Yeah, you have to evaluate for the parent also. So, this will be 1 by 9 for 0 0 0, 0 0 1 will be 1 by 8, 1 0 0 will be 1 by 5, and 1 1 1 will be 1 by 40, right. So, now I have all the fitnesses, tell me how to pick.
100 will be 1 by 7, right?
100 will be 1 by 100 is 4, no? So, 7, yeah.
So So since the mutation possible is random, why can't we just eliminate the population, the initial population, the previous population?
Why?
Information if it's more.
If we have a good solution.
That doesn't really come.
No, why are you throwing away any information? So, maybe hold on to your question. How do you do the selection? How do you use the fitness to make a selection?
Highest fitness value.
You say you can, so one way you can do is, you go for what's known as an elitist selection. Meaning, what's the best guy here? 1/7. And you just make copies of this. This is one way. This is called elitist selection. What is the problem with this? Is there a problem with this?
Yeah.
This is like as aggressive as hill climbing. You know, I'll only take the best. I'm forgetting any other variety that I have, and so on and so forth. Right? So that's a potential problem with this. Right? On the other hand, you can do something called tournament selection. Meaning you pick a bunch of solutions. What do I mean by bunch? It's a hyperparameter. You have to choose that bunch. So what is the size of that bunch? That size could be 2, that size could be 1, that size could be 5. So you pick a bunch of solutions and then you basically have them play a tournament against each other, like a fitness tournament, and you pick one of them or two of them. So you can choose something like that, right? That is one way. The best way is something known as roulette, or more technically very Barabasi Albert type, right. So you pick a solution in probability proportional to its fitness. Higher the fitness, higher the probability. So you could probably just normalize all of these. Think of these as your degrees for your Barabasi, and you would compute the probabilities, right. So 1/8 by sigma fitness will give you fitness of this. So you pick that with a particular probability. So better solutions. So this is very Darwinistic, right. So higher, better individuals with higher fitness have higher probability of survival of the fittest. So all of these will have advantages and disadvantages. So and I can give a name to each of those things. You know, somebody would have already come up with this strategy. So there is no, I think I want you to particularly embrace the concept here rather than the exact algorithm, because I don't think there is a genetic algorithm. There are genetic algorithms, right. You can mix and match any of these recipes to come up with something that is best suited to your problem. What kind of fitness, fitness is the one thing that is non-negotiable, right. Fitness is well defined by your, so here in our case E theta will be the 1/E theta will be the fitness, or minus E theta, whatever, right. That will be your fitness. Wherever, but in this, in every different case, for IPL there will be a different kind of fitness, for some other TSP there will be a different kind of fitness, so on and so forth. So the important concept to remember is that you need these operators that cause variation. So how does this compare with what we asked of yesterday? Ability to handle non-differentiable, non-linear, multimodal cost functions, parallelizability, few control variables. What are your control variables?
Hyperparameter.
Hyperparameter.
Population
Yeah,
size.
what are they? What are they?
Population.
Like number of iterations.
That is number of generations, population size.
size.
Method of selection. And
Okay, even before that, mutation rate, crossover rate.
Mutation rate.
How often do you mutate? How often do you crossover?
So, but mutation after every generation you are going to do, right?
Yeah, but how many individuals do you mutate, right? So you typically, like in biology, you say n mu equals 10. What does n mu equals 10 mean?
1 in every 10.
One. Right? So for a population of size n, I will mutate 10 people. So I will mutate 10 people every generation. N mu equals 10 means. N mu equals 1 is actually a very special case. N mu equals 1 has very different evolution characteristics, evolution trajectories compared to other things. In today's video, I hope you got an introduction to the challenges that are involved with representation and some example representations, and also an illustration of how we go about solving with a genetic algorithm. In the next video, I will introduce you to another evolutionary algorithm, namely differential evolution, which is a very powerful algorithm especially for handling biological data sets, for biological parameter estimation and so on. And we will also look at some of the challenges in implementing evolutionary algorithms, and we will discuss as to when EAs are actually useful.